Hello, I'm going to show you how to do a trick. This is the calendar trick. Now you may have seen this before. What happens is if somebody gives you their date of birth, you can tell them the day of the week on which they were born. Now this is a fun trick to do with friends and family and only involves some simple arithmetic. What it doesn't involve is memorizing 100 years of calendars. In fact, there are only 12 things to memorize. These are the days of the week the months began with in 1899. Now why 1899? Well, to work out any date in the 20th century, we're going to memorize this table and add on from there. So January started with a Sunday, February started with a Wednesday, and so on. But it would be helpful if we had some easy way to remember this table. So let's encode the days as follows. Sunday is the first day of the week, Monday is the second day of the week, so on up to Saturday. But because we're mathematicians, we like to start counting from 0. So I'm going to change Saturday to 0. Ping, like that. Then the table itself becomes this. Now, as you can see, the first row looks like 144. That's 12 squared. The second row now looks like 25. That's 5 squared. Third row looks like 36. That's 6 squared. And the fourth row now looks like 146. That's 12 squared plus 2. Well, that's just a way to remember that table. But let's do an example. Here's an example, the 9th of May 1941. Now, May was in the second row of that table, and in fact, it was a 2. Now, let's consider the year component of the date, 1941. But first of all, before I do that, I want to ask a question. How long is a year? Well, if you measure it from the beginning of a season to the next season, then as defined by atomic clocks, it is 365 days, 0.24. So it's incredible then that the ancient Romans had a 355-day calendar. That's 10 days out of sync. In fact, what they did is have a leap month that they used to inject to realign themselves with the seasons. But this was badly managed, so in 45 BC, Julius Caesar, looking slightly scary there, and his mathematicians introduced a new calendar. This had 365 days with a leap day every 4 years. So if you work out the average year over a period of 4 years, it would look like this. You would have 365.25 days and a quarter days. And this was far more accurate. In fact, all you gain is 11 minutes a year. But then again, those minutes add up, and in fact you gain a day every 134 years. So by the time of the 16th century, the calendar had become 10 days out of sync with the seasons. This led Pope Gregory XIII, there he is, looking slightly like a grumpy Santa Claus, and his mathematicians to introduce a new calendar in 1582, and the rule was this: a year was 365 days with leap days every 4 years, unless the year was divisible by 100. So centuries like 1700, 1800 and 1900 were not leap years, but we still had leap years if the century was divisible by 400. So 1600 and more recently 2000 were leap years. Now, if we work out the average year over a 400-year period, it worked out to be 365 days, 0.24. And this is a far more accurate measure and would remain so for centuries to come. So it's incredible then that Britain didn't adopt this calendar for another 170 years. When the date went from Wednesday the 2nd of September 1752 to Thursday the 14th of September 1752. In fact, Britain and Europe were operating 2 different calendars during that time. This is why the Spanish writer Cervantes and Shakespeare apparently died on the same day, the 23rd of April 1616, when in fact Cervantes died 10 days before Shakespeare. This is because Spain was using the Gregorian calendar and Britain was using the Julian calendar. But still, this coincidence has led the United Nations and UNESCO to name the 23rd of April World Book Day. But what have we learned? One calendar year is 365 days. In other words, that's 52 weeks and 1 day. So every year, the day moves on 1. So back to the trick. After working out the month, we add on 1 for every year. So for 1941, we add on 41. Now we have to work out the number of leap days. Well, to calculate the leap days, we divide the year by 4, ignoring any fractions. So for 1941, we add on 10. Now we simply add on the date, which is a 9, and we get the answer 62. So what does that mean? Well, if you add on 7 days, you get back to where you started. Monday plus 7 days is a Monday again. So, in fact, we can ignore each multiple of 7. So let's write 62 as 56 plus 6. That's 8 weeks plus another 6 days. Then we can ignore 56, and 6 is the number we're interested in. This is called modular arithmetic. The idea is this. It works like a clock. Imagine a clock on a wall. Then if you add 12, you're going to get back to where you started. In this case, we're going to have a clock of 7 numbers, like this. And if we add 7, we get back to where we started. So for this reason, modular arithmetic is sometimes called clock arithmetic. But if we write this equation at the bottom in modular arithmetic, it looks like this. We can ignore 56. We have a super equal sign there with 3 lines. 6 is the number we're interested in, and this, mod 7, at the end, tells us that we're using a clock with 7 numbers on it. And that's our final answer, 6. So if we go back to the legend we had before, 6 was the 6th day of the week, which was a Friday. So the 9th of May, 1941, is a Friday. And that was the day the Enigma machine was captured.